Ever feel like AI is evolving faster than you can keep up? Like 1 minute it's writing poems, the next well, we'll get to that. Today we're diving deep into some seriously cool advancements that are pushing the boundaries of what's possible.
Exactly. We're talking about making AI smarter, faster, and more adaptable. Think of it like giving your brain a serious upgrade. So what's on the agenda?
First up, we're unpacking a new way to edit AI knowledge, kind of like surgically removing outdated info without messing up everything else. It's called BaFT, which stands for Basis Level Representation Fine-Tuning. Basically, it's a clever method for updating what an AI knows without breaking it.
Then we're tackling the challenge of AI that can actually use tools. We'll explore ToolDial, a new dataset designed to help AI learn how to ask the right questions and use external tools to solve problems. Think of it as teaching AI to use a Swiss Army knife.
Next, we're speeding things up with duodecoding, a hardware trick that makes AI run faster by splitting the work between different parts of your computer. It's like having two engines in your car, working together to get you to your destination quicker.
After that, we're getting personal with Proper, a framework for tailoring AI to individual users. It's all about making AI that understands your specific needs and preferences. Imagine a personal AI assistant that actually gets you.
And finally, we're coding it up with CodeCode, a massive new dataset for training AI to write code. This is like giving AI a huge library of code examples to learn from, so it can become a coding whiz. Buckle up, it's going to be a wild ride. All right, let's dive into this paper on knowledge editing in large language models. The title is quite a mouthful: Unlocking Efficient, Scalable, and Continual Knowledge Editing with Basis-Level Representation Fine-Tuning.
Sounds ambitious. So what's the core problem they're tackling?
Basically, LLMs are trained on static data, but the real world is constantly changing. This means their knowledge can quickly become outdated, leading to factual errors or even harmful outputs.
Right, like an LLM still thinking Pluto is a planet.
Exactly. So knowledge editing aims to update specific facts in an LLM without messing up everything else it knows. The challenge is making these edits selective and efficient.
And what have previous approaches tried?
Many methods focus on updating a small number of parameters in specific layers of the LLM. The idea is to target the parameters responsible for storing the knowledge you want to change.
Makes sense. But the paper suggests there's a trade-off?
A big one. It's called the editing locality trade-off. If you aggressively edit to ensure the new knowledge is learned, you risk corrupting other unrelated knowledge. It's like fixing one line of code and breaking 10 others.
Ouch. So what's causing this trade-off?
The authors argue that parameter-based updates have a global effect. Edited parameters affect all inputs indiscriminately. They question whether targeting specific parameters truly benefits editing if those parameters influence everything.
Okay, I see their point. It's like using a sledgehammer when you need a scalpel.
Precisely. That's where representation fine-tuning comes in. Instead of tweaking parameters directly, they modify the representations, the internal activations, within the LLM.
How does that work?
They apply a linear update to a few representations in a learned subspace. Think of it as nudging the LLM's internal understanding in a specific direction, but only in certain contexts.
So it's more targeted than parameter updates.
Potentially, yes. A method called ReFT, representation fine-tuning, already does this, showing promise. However, this paper argues that even ReFT's linear updates have limitations.
Another trade-off?
Yep. The authors theoretically show that this linear update imposes a tension in the editing locality trade-off. Even though ReFT is more selective than parameter updates, its subspace-level control can still be too coarse for precise knowledge editing.
Subspace-level control, what does that mean?
Imagine the LLM's understanding of a concept as a point in a high-dimensional space. ReFT adjusts this point within a specific subspace, a lower-dimensional slice of that space. The problem is this slice might still affect other unrelated concepts.
So even with ReFT, you can accidentally modify things you didn't intend to.
Exactly. The paper formalizes this with a theorem showing that if BaFT achieves good generality, meaning it can generalize the edit to different phrasings, it inevitably hurts the locality of some irrelevant knowledge.
That's a bummer. So what's their solution?
They propose BaFT, basis level representation fine-tuning. It's designed to break the linearity of BaFT and provide more precise updates.
Basis level? Sounds like linear algebra is involved.
You got it! The subspace BaFT uses is spanned by a group of basis vectors. BaFT computes a weight for each basis based on the input representation. This input-dependent weighting allows BaFT to manage different types of knowledge in an adaptive way.
So instead of adjusting the entire subspace, it adjusts individual components of it based on the specific input.
Precisely. It's like having individual knobs for each dimension of the subspace, allowing for much finer-grained control.
How does this weighting mechanism work?
BaFT learns a weight for each basis vector. This weight determines how much that basis contributes to the update for a given representation. If a basis is deemed unimportant for a particular edit, its weight will be low, minimizing its impact.
So it's like a dynamic filter that selectively activates different parts of the subspace?
Yes, and the cool thing is if all the basis vectors have the same weight, BaFT reduces to BaFT, so BaFT is a generalization of BaFT.
Okay, that's clever. How do they train BaFT?
They use a combination of losses. First, a teacher-forcing loss to ensure the LLM learns the new knowledge. Second, an incremental load balancing loss to encourage different bases to be used for different edits, preventing the model from relying on just a few fixed bases.
What's the point of that load balancing loss?
Without it, the model might just use a small subset of bases for all edits, effectively reducing BaFT to a smaller, less expressive BaFT model.
Ah, I see. Keeps things diverse.
Exactly. And finally, they can optionally use a locality regularization loss if they have examples of irrelevant knowledge. This encourages BaFT to minimize the impact on that irrelevant knowledge.
So it's actively trying to preserve what it already knows.
Yep. It encourages the weights for irrelevant knowledge to be small, while ensuring the weights for editing knowledge are large enough. It's like telling the model, focus on this and leave that alone.
Sounds promising. What were the experimental results?
They tested BaFT on 3 LLMs, Llama 2, Llama 3, and Gemma, and 5 knowledge editing benchmarks. The results consistently showed that BaFT achieves a better editing locality trade-off than existing methods.
Better in what way?
It maintains high reliability, meaning it successfully learns the new knowledge while also preserving locality, meaning it doesn't mess up unrelated knowledge. And it does this with better parameter efficiency than many other methods.
Parameter efficiency is key, especially for large models.
Absolutely. They also compared BaFT to ReFT, showing that BaFT consistently achieves better locality and portability, the ability to transfer new knowledge to related content without sacrificing reliability.
So the basis level weighting really makes a difference?
It seems so. They even visualize the basis weights, showing that BaFT evenly distributes the editing over all bases and assigns significantly lower weights to unrelated knowledge.
That's a nice confirmation of how it's supposed to work.
They also tested BaFT in continual editing scenarios, where multiple pieces of knowledge are updated sequentially. BaFT showed excellent robustness against forgetting, maintaining high locality even after many edits.
Forgetting is a big problem in continual learning, so BaFT handles it well?
It seems to, and it does so with significantly fewer parameters than some other continual learning methods. It's a good balance of effectiveness and efficiency.
Any limitations to the study?
They acknowledge that the benchmarks they used might not fully reflect the diversity of real-world applications. Also, BaFT, like ReFT, requires hyperparameter tuning to determine the best layers and positions to add interventions.
So there's still room for improvement?
Definitely. They plan to explore automating the selection of intervention points and investigating whether representation-based methods can learn all the edits that parameter-based methods can.
Overall, it sounds like a promising approach to knowledge editing.
I agree. BaFT's basis-level control offers a more fine-grained way to update LLMs, potentially mitigating the editing locality trade-off and enabling more efficient and reliable knowledge updates. All right, let's dive into this paper on ToolDial. It's all about making tool-augmented language models, or TALMs, better at having real conversations.
Tool-augmented, so like giving AI access to external tools to answer questions. Why is that a problem right now?
Exactly. The issue is that current datasets for training these TALMs are too simple. They don't capture the back and forth we see in real life, where the AI needs to ask for clarification or proactively find more info.
Ah, I see. So it's like the AI is stuck in one-turn interactions when it needs to be playing the long game.
Precisely. That's where ToolDial comes in. It's a dataset with over 11,000 multi-turn dialogues, averaging about 9 turns each. These dialogues incorporate 16 different actions from both the user and the system.
16 actions. What kind of actions are we talking about?
Things like request, where the system asks for more info, clarify when the user's intent is vague, or even fail inform when the user can't provide the needed data.
Okay, that sounds way more realistic. So how did they create these dialogues?
They built an API graph first. Think of it as a map connecting different APIs based on whether one API's output can be used as input for another. This helps simulate scenarios where the AI needs to chain multiple APIs together.
API chaining. That's clever. So if the user doesn't provide all the info, the AI can use another API to fill in the gaps?
Spot on. They then defined those 16 user and system actions and created 23 plausible sequences of these actions. These sequences act as a skeleton for the dialogues.
So they pick a pair of APIs from the graph, choose an action sequence, and then flesh it out with dialogue states and actual conversations.
You got it. They use GPT-4o to convert these augmented action sequences into natural-sounding conversations. The goal was to do this with minimal human effort.
And what did they find when they tested language models on ToolDial?
Well, modern language models struggled, especially with dialogue state prediction. Their performance dropped as the dialogues got longer. They also had trouble predicting the next action, particularly when it involved requesting input parameters or asking clarifying questions.
So the AI was basically guessing instead of strategically gathering information.
In a nutshell, yes. Smaller models like Llama generally underperformed compared to the GPT models. However, fine-tuning Llama on ToolDial significantly improved its performance.
That's encouraging. So ToolDial can actually help improve these models.
Exactly. The paper highlights that ToolDial is a valuable resource for both assessing and improving TALMs in complex multi-turn interactions.
It sounds like a crucial step towards making AI assistants that can actually handle real-world conversations and tasks.
Definitely, it's about moving beyond simple queries and building AI that can truly understand and respond to our needs in a dynamic way. Okay, let's dive into this paper. Duo-decoding hardware-aware heterogeneous speculative decoding with dynamic multi-sequence drafting. It's all about speeding up large language model inference, which, as we know, can be a real bottleneck.
Exactly. LLMs are amazing, but they're computationally intensive. This paper tackles that head-on. So what's the core problem they're addressing?
The main issue is the autoregressive generation process. LLMs generate text token by token, meaning they have to do a full forward pass of the model for each new word. That's slow. Speculative decoding is a promising approach to reduce this latency.
Right, speculative decoding. Can you break that down for our listeners?
Sure. Speculative decoding uses a smaller, faster draft model to predict multiple tokens at once. Then, the original, larger target model verifies these predictions in parallel. It's a draft-then-verify framework.
So the draft model proposes and the target model approves or rejects. Sounds efficient. But what's the catch?
The draft model itself introduces overhead. It adds to the computational burden, increases GPU memory usage, and can even slow down the time to first token, or TTFT. That's the time it takes to generate the very first word, which is crucial for interactive applications.
Ah, so the draft model, meant to speed things up, can become a bottleneck itself. That's where duo-decoding comes in, right?
Precisely. Duo-decoding's key idea is to run the draft model on the CPU and the target model on the GPU. This allows for parallel decoding, shifting the draft model's overhead to the CPU without sacrificing draft quality.
Interesting. So they're leveraging heterogeneous hardware, CPU and GPU, to their advantage. Why does this work?
The assumption is that the draft model can still generate tokens reasonably fast on the CPU. The paper provides empirical evidence showing that the time it takes the draft model to generate tokens on the CPU is comparable to the target model's verification time on the GPU.
Okay, that makes sense. So what are the main components of duo decoding?
There are three main parts: heterogeneous parallel decoding, dynamic multi-sequence drafting, and a modified verification process. The parallel decoding is what we just discussed, running the draft and target models on different hardware. Then they use a hardware-aware optimal draft budget to minimize idle time on either the CPU or GPU.
A draft budget? What's that?
It's the number of tokens the draft model generates in each iteration. They calculate an optimal budget based on the relative speeds of the CPU and GPU to keep both devices busy.
Got it. So they're trying to balance the workload. What about this dynamic multi-sequence drafting?
As the draft budget increases, the acceptance rate of later tokens in the draft sequence tends to decrease. To combat this, they generate multiple draft sequences based on the uncertainty of the draft model's outputs.
Uncertainty. How do they measure that?
They use the predicted probabilities from the draft model as a proxy for acceptance rates. Higher probabilities indicate greater confidence and a higher likelihood of being correct. They use a threshold based on the probabilities of the first two tokens to decide whether to continue a sequence or start a new one.
So if the draft model is confident, it keeps going. If it's uncertain, it explores different possibilities. Clever. And the verification process?
They adapt the verification process to handle the multiple draft sequences. Since the draft and target models receive the same inputs, some draft tokens might not be verified in the same iteration they're generated. So, they prioritize verifying tokens from the previous iteration first.
Okay, it sounds like a well-thought-out system. What kind of results did they achieve?
They saw significant speedups across 7 different tasks, up to 2.61x faster than standard autoregressive generation. They also reduced the time to first token by 17% compared to conventional speculative decoding.
Impressive. So it's not just faster overall, but also quicker to get that initial response. Did they compare against other methods?
Yes, they compared against vanilla autoregressive generation, standard speculative decoding, and other techniques like prompt lookup decoding, PLD, retrieval-based speculative decoding, REST, and look-ahead decoding. Duo decoding consistently outperformed them all.
And they did ablation studies to confirm that each component of duo decoding contributes to the overall performance.
Exactly. They showed that dynamic multi-sequence drafting and the hardware-aware drafting budget both play a crucial role in achieving the best results.
It sounds like a really promising approach to speeding up LLM inference. What are some of the limitations they mention?
They didn't explore performance with large batch sizes. They only tested target models with 7B parameters, and their evaluations were limited to a single hardware configuration. So there's still room for future research to see how well duo decoding scales and performs on different systems.
Right, those are important considerations. But overall, duo decoding seems like a significant step forward in making LLMs more practical and efficient.
All right, let's dive into this paper on personalized large language models. The title is Proper, a Progressive Learning Framework for Personalized Large Language Models with Group-Level Adaptation. It's all about making LLMs more tailored to individual users.
Personalized LLMs, huh? That's a hot topic. So what's the core problem they're trying to solve?
The big issue is data sparsity. When you try to personalize an LLM for a specific user, you often don't have enough data about that user to really capture their preferences. Think about it. These models are trained on massive data sets, but individual user histories are usually pretty small.
Makes sense. So how does this proper framework tackle that data sparsity problem?
They're taking inspiration from social science, specifically something called meso-level theory. The idea is to bridge the gap between population-level data and individual user data by introducing a group level. They group users with similar preferences and then adapt the LLM in stages.
Okay, so it's like saying, instead of going straight from a general model to a user-specific one, let's create intermediate models for groups of users with shared interests.
Exactly. They use a mixture of experts, MO structure, combined with low-rank adaptation, LoA. Let's break that down. MoE means they have multiple experts, each representing a user group. LoRa is a technique for efficiently fine-tuning large models without changing all the parameters. It focuses on the most important ones.
So each expert in the MoE is a LoRa-adapted version of the main LLM, fine-tuned for a specific group of users?
Precisely. And they use a user-aware router to automatically assign users to the most appropriate group. Then they have a LoRa-aware router to integrate the individual user's LoRa with the group-level LoRa.
A router for routers. Sounds complex. What's the point of having two routers?
The first router, the user-aware one, figures out which group a user belongs to. The second one, the LoRa-aware router, is more about fine-tuning the model based on the user's specific data, taking into account what the group already knows. It's like saying this user is in this group, but they also have these unique characteristics.
Got it. So it's a hierarchical personalization process. What are the actual stages in proper?
3 stages. First, they adapt the LLM to the task in general. That's the population level. Second, they adapt it to user groups using LoRa and MoE. And third, they adapt it to individual users, again using LoRa. Each stage builds upon the previous one, refining the model's understanding of user preferences.
And they're using LoRa in each stage to keep things computationally efficient, right?
Exactly. LoRa is key to making this practical. It lets them personalize the model without retraining the entire thing from scratch for every user or group.
So how well does it actually work? What kind of results are they seeing?
They tested it on the LAMP benchmark, which is specifically designed for evaluating personalized LLMs. And they found that Proper significantly outperformed other methods, especially in situations where user data was scarce. They saw improvements across multiple tasks.
That's promising. Data sparsity is a real bottleneck in personalization. What kind of tasks did they test it on?
A mix of things: personalized citation identification, movie tagging, product rating, news headline generation, scholarly title generation, and tweet paraphrasing, so both classification and generation tasks.
Okay, a pretty diverse set of tasks. Did they dig into why Proper works better? Any insights into the group-level adaptation?
They did some ablation studies, which is where they remove parts of the model to see how it affects performance. They found that both the user-aware router and the LoRa-aware router were important. They also visualized the user embeddings and expert weights, and it showed that the experts were indeed learning distinct group preferences.
So the groups aren't just random collections of users. They actually represent meaningful clusters of preferences?
That's the idea, and their visualizations support that. They also did a case study where they showed how the model's output gradually became more personalized as it went through the 3 stages of Proper.
Interesting. What are some of the limitations of this work?
They point out a few. First, they evaluated the model on separate tasks, but in the real world, user preferences often carry over between tasks. Second, they assume user preferences are static, but people change over time. And third, the 3-stage process adds some extra training time and parameters.
Those are valid points. The static preference assumption is a big one. People's tastes and interests evolve constantly. What about ethical considerations?
They address that too. They talk about privacy concerns, the potential for bias in user data, and the need for transparency and user control. Personalized models rely on user data, so it's crucial to have safeguards in place to protect that data and ensure fairness.
Definitely. Responsible development of personalized LLMs is essential. So overall, what's the takeaway from this paper?
Proper offers a promising approach to personalized LLMs by addressing the data sparsity problem with a progressive learning framework and group-level adaptation. It's a step towards more efficient and effective personalization, but there's still work to be done on things like dynamic preferences and ethical considerations. All right, let's dive into this paper on code. It's all about creating a synthetic dataset for training large language models specifically for coding. The big problem they're tackling is that existing datasets either don't cover enough ground in terms of coding challenges, or they can't reliably verify if the code is actually correct.
Yeah, I've seen that issue. You get these massive datasets, but how much of it is actually good data? It's like quantity over quality. So what makes Cod Code different?
Cod Code aims to be both broad and verifiable. It's a synthetic dataset, meaning it's generated by AI, but it's designed to cover a wide range of coding tasks, from basic stuff to complex algorithms. And crucially, it uses a self-verification process to make sure the solutions are correct.
Self-verification. How does that work?
Okay, so the process has three main steps. First, they synthesize a bunch of coding questions. Then, they generate solutions and unit tests for those questions. Finally, they run the unit tests to check if the solutions are correct. If a solution fails, they give it another shot, especially if it seems like a challenging problem. Only the question-solution test triplets that pass this verification are kept in the dataset.
So it's like the AI is grading its own homework, but with a built-in system to double-check the answers. That's pretty clever. What kind of benchmarks are we talking about here?
They tested it on a bunch of well-known coding benchmarks like HumanEval, MBPP, Big Code Bench, and Live Code Bench. And the models fine-tuned on Cod Code actually beat other models like Qwen and DeepSeek on most of these benchmarks.
That's a strong claim. So let's break down these steps a bit more. How do they actually synthesize the coding questions in the first place?
They use a mix of methods to ensure diversity. For simple questions, they use a technique called Magpie prefill, which is basically filling in the blanks in a chat template with a predefined suffix like write a Python function that, and letting the LLM complete the query.
Okay, that makes sense for the simpler stuff. What about the more complex questions?
For those, they leverage existing human-written coding assessment datasets like LeetCode and Codeforces as seed corpora. They then prompt a teacher LLM, in this case GPT-4o, to act as an expert programming instructor and generate new assessment questions that are similar in difficulty and scope to the seed questions.
So it's like using the existing datasets as a blueprint to create more questions of the same caliber. What about data structures and algorithms? Those are crucial for coding competence.
Exactly. They convert Python DSA knowledge into assessment questions by sampling DSA code snippets and prompting the LLM to craft questions that test foundational understanding, but without directly replicating the code.
That's smart. You don't want the model just memorizing code. You want it to understand the underlying concepts. What about package-specific knowledge? That's a big part of real-world coding.
They've got that covered too. They transform technical documentation from popular Python libraries like Flask, Pandas, and PyTorch into coding questions. They even have a quality control mechanism that allows the model to abstain if the documentation isn't sufficient for crafting a high-quality question.
So it's a pretty comprehensive approach to generating diverse coding questions. What about the solution and test generation? You mentioned a self-verification process.
Right? They use GPT-4o to generate both the solution and the unit tests for each question. Then, they execute the unit tests to validate the correctness of the solution. Only the question-solution test triplets that pass this self-verification are retained.
But what if a question is genuinely challenging and the model just can't get it right on the first try? Does it just throw it away?
That's the clever part. Instead of discarding those challenging questions, they allocate additional self-verification attempts. They allow up to 10 attempts to generate a solution that passes the unit tests. This way, they preserve the challenging questions and naturally assign difficulty labels based on the success rate across attempts.
So, the more attempts it takes to get a correct solution, the harder the question is considered to be. That's a really elegant way to handle difficulty. What about making the data more suitable for post-training?
They address the gap between coding questions and training data by using an LLM-based style converter to reformat each question. They structure them as Python completion tasks with function signatures and examples. This makes the data more readily available for reinforcement learning training.
So it's about making the data more aligned with how the model will actually be used in practice. What about chain of thought reasoning? Is that incorporated?
Yes, they generate an SFT dataset by leveraging the questions and using DeepSeek R1 as the response generator to create chain-of-thought responses. They use test-based reject sampling to ensure the quality of these responses.
Okay, so they're really trying to cover all the bases here. Diverse questions, verifiable solutions, and data formatted for different training methods. What kind of analysis did they do to validate their approach?
They did a bunch of pipeline analysis. They evaluated the reliability of their self-verification pipeline using the MBPP validation dataset. They also assessed the impact of allocating more attempts to challenging questions, and they performed statistical analyses of Codcode's token length, diversity, difficulty distribution, and potential contamination with existing benchmarks.
Contamination is a big concern with synthetic datasets. You don't want the model just memorizing answers from the training data. What did they find?
They found that the contamination rate was minimal, with only a small number of potentially contaminated questions. Most overlaps occurred between the simpler questions and simple Python questions from human-evil MBPP, and they excluded these cases from their performance evaluation.
That's good to hear. So overall, it sounds like Codecode is a pretty robust and well-designed synthetic dataset for training coding LLMs. The self-verification process and the focus on diversity and difficulty seem to be key differentiators.
Wow, that was quite the journey through the AI landscape. From surgically updating knowledge and language models to teaching AI to wield tools like a pro, it's clear things are moving at warp speed.
Absolutely. I'm still wrapping my head around the idea of AI not just knowing facts, but also knowing how to find them and use them effectively. That ToolDial dataset seems like a game changer for building truly helpful AI assistants.
And the hardware innovations. Who would have thought splitting the workload between the CPU and GPU could lead to such significant speedups? That Duo decoding paper really highlighted the importance of thinking outside the box when it comes to optimizing AI performance.
Definitely. And then there's the push for personalization. That framework for tailoring AI to individual users really resonated. It's exciting to think about AI that truly understands our unique needs and preferences.
It's not just about understanding, but also about adapting and evolving with us. The idea of AI learning and growing alongside us, constantly refining its knowledge and skills, is incredibly powerful.
And let's not forget about the coding front. That massive data set for training AI to write code is mind-blowing. Imagine the possibilities when AI can not only understand code, but also generate it efficiently and accurately.
It feels like we're on the cusp of a new era of AI, one where it's not just a tool, but a true partner, capable of collaborating with us on complex tasks and solving real-world problems.
It's a little daunting, sure, but also incredibly exciting. There are still plenty of challenges to overcome, but the progress we're seeing is undeniable. I can't wait to see what the future holds.
Me neither. Thanks for joining us on this deep dive. We'll be back soon with more explorations into the ever-evolving world of AI.